two blocks of masses 1 equal 5 kilogram and mass 2 equal 10 kilogram are roped together on an inclines, both having different angles. So the first block's on an incline of 50 degrees, and the second block's on an incline of 20 degrees. Now they also each have different masses, as we said before, 10 kilograms, 5 kilograms. So, assuming the rope and pulley are massless and the inclines and pulley are frictionless, what acceleration will they experience? What must be the tension in the rope? So first of all, what we're going to do, very first thing, we've got force of gravity pulling down on both of these, right? But the force of gravity isn't really what matters. What matters is how much of it gets canceled out and how much is parallel. So remember, whatever the force of gravity is perpendicular, force normal, they're going to cancel each other out. So while they're still present, for our purposes, we're just not going to pay attention to them because they're not going to have any effect on what we're doing. Force of gravity perpendicular over here gets canceled out by the force of by the normal force, because the normal force is able to cancel out whatever's perpendicular. So the normal force cancels out the force of gravity perpendicular to the side of the triangle. So once again over here, we're not going to worry about these for our problem's purposes. All right, so that leaves us, the only thing we're really concerned about is what is the parallel component. Up here, we've got a 20-degree angle. Over here, we've got a 50-degree angle, as we've reasoned before in previous lessons. So sine 50 times whatever the weight it experienced here is, Fg, and over here, it's going to be sine 20 times Fg. We haven't figured out Fg yet, but that'll take no time at all. Fg is equal to 5 times 9.8, which is equal to 49 newtons. Over here, Fg is going to be equal to 10 times 9.8, which is going to be equal to 98 newtons. So if we want to figure out what the parallel components are, we just plug it into our calculator. We get that sine 50 on this one, it's going to be equal to the force of gravity on the first block parallel to the triangle. Getting kind of complicated, but its weight, the amount that's pulling down the side of the triangle, is going to be equal to, once we plug that into our calculator, 37.5 newtons. Over here, we're going to get that the force of gravity on the second block, parallel, is going to be equal to 33.5 newtons. All right, so we've got what the two parts are parallel. So which direction can we expect to move in? We know that we're going to have to move in this direction because there's more force in the system pulling this way than this way. It's a smaller one, so this is the side that's going to win. All right, so with some of this work in hand, we're going to start to do it, complete it. All right, so let's finish this up. We know that the parallel force, which is the only force we have to worry about because we know that gravity, the gravity perpendicular and the normal force cancel one another out. We know that this force of gravity 1 parallel is going to be equal to 37.5 newtons. Force of gravity on 2 parallel is going to be equal to 33.5 newtons. All right, now we want to find out what's our acceleration. What's the tension in the rope? So there's going to be tensions pulling both this way. Now, as we've talked about before, we can actually treat this whole thing as a big system. So we've got one big system. So we can figure out the tensions and come up with a bunch of equations, but there's no reason to because we know that what's the external forces acting on it? The tensions aren't external. They're the thing that links our system, that makes it a system. So the tensions aren't going to cancel out whether or not we can treat it as a system. They're what enables us to use it as a system. So we only have to pay attention to what's working outside if we treat it as one big system. So what forces are acting on the system is going to be equal to the mass of the system times whatever the acceleration is. And they're linked. We've got a rigid connection here. Unlike the baboon and crate problem, we've got a linked rigid connection here. If one thing moves, the other one has to move. So we know that we can use the same acceleration for the two of them. So what forces are here? Let's make to the right is normally our positive, so we'll keep that as our positive. So we've got 33.5 pulling in the right minus 37.5 newtons is equal to, what's the mass of each piece? Well, 10 plus 5 times our acceleration. So we start solving things out. And we've got -4 equals 15 times the acceleration, which gives us that -0.27 meters per second equals our acceleration, which makes sense because as we talked about before, we're going to see an acceleration pulling things that way. In this case, it's a very small acceleration, but it is still pulling it along. All right, so this is what our acceleration is. It's parallel. It's not just some general acceleration. This is a magnitude. And what we know if we want to consider it as a vector, it's the amount parallel to the triangle and pulling to the left. And it's going to be parallel from both of their point of view. So they're going to have very different acceleration vectors. This one's only going to come up at a 20-degree incline, whereas this one's going to be going down at a 50-degree incline. And so one's rising and the other's falling. But as we talked about before, since the only thing affecting this is the parallel component, because remember, the normal force cancels out the perpendicular component of gravity, the only thing we really have to worry about here is what the total acceleration is, and it's up to us if we had a problem that then had to make us consider which direction it was moving, then we'd have to work on it. But in this case, it's enough to say that it's -0.27 meters per second, or really 0.27 meters per second, and then talk about what direction it's moving in. Now, what if we want to solve for what the tension in it is? Well, if we want to solve for what the tension is, so what's the tension going to be equal to? Well, we can look at just a single block on its own. So let's consider looking at the smaller block. So the smaller block is being pulled down with 37.5 newtons. And it's being pulled up with tension. We don't know what that tension is yet, but we'll figure it out in just a sec. So 37.5 newtons. And another important thing is because the way we've got this constructed, tension is parallel. We've got tensions as being parallel. Now, as we've talked about before, it's possible for a rope to be pulling at a different angle and cause things to not be parallel to the surface. But in this case, we've set up our problem in such a way, or our problem was given to us in such a way that the rope was going to run parallel to the surface, so we don't have to worry about this. So it's just going to be these two things acting directly without having to worry about putting in any more angles. We already figured out that this one was the parallel component, so we're good to go from here. So this is the negative direction, so tension's pulling in the positive direction, -37.5. That's the sum of our forces on the little block is going to be equal to the mass of the little block, because we're just looking at the little block now. If we looked at the system, we wouldn't be able to see the rope anymore because it's what makes it a system, so we have to look at it piecemeal. So the tension minus 37.5 is equal to the mass of the little block, which is 5, times the acceleration of the little block. The acceleration of the little block, we just solved for it, is -0.027 meters per second. And so, oh, whoops, sorry, not -0.027, but simply -0.27 meters per second. We now solve this out algebraically. We get T is equal to 36.15 newtons, which makes sense because the tension in the rope is going to have to be less than the force of gravity parallel. Otherwise, it's going to go in the direction of tension. The larger force is the one that's going to win out and be able to have the effect if they're directly opposed. So tension's smaller than the acceleration, smaller than the force caused by gravity. And that gives us everything for this problem, and we've got it solved. I hope you learned something. There's a bunch of different possibilities and really advanced examples that there can be with forces, but just by breaking it down into a good free body diagram, carefully analyzing the forces involved, putting down all the things that you know, you can work your way through it and you can figure out what you're going to do. I hope you enjoyed it, and we'll see you at Educator.com for the next lesson. Goodbye.